Welcome to Maths with EJD. In this video, we'll be talking about duality in linear programming. And let's look at the introduction. In linear programming, duality is a fundamental concept that links every optimization problem, referred to as the primal problem, with a corresponding, okay, like in my usual fashion, right? I like to emphasize these key terms. So primal problem, okay, with a corresponding dual problem. So the original problem you have is called the primal problem, but then you can transform it into a dual problem. Okay. Now, this relationship helps us better, helps us better understand the structure of optimization problems and offers methods for more efficient problem solving, Now, duality duality also provides a deeper insight into how changes in constraints, into how changes in constraints or the objective function or the objective function affect the optimal solution. In the previous video, we talked about um, you know, the idea of the idea of sensitivity analysis. Okay, and we saw that in carrying out sensitivity, we look at how changes in the objective function coefficients and in the constraint limits can actually affect the optimal solution. In the same way, duality can affect the optimal solution, and that's the essence of what we are considering now. So let's see the definition now. What is the definition of the dual problem? Okay, so for every primal problem, for every primal, let me just keep emphasizing, right? For every primal problem, there is a corresponding dual problem. Like we said before, there is a corresponding dual problem. Okay. So the dual problem is formulated using the data, isn't the data from the primal problem. and the structure of the primal and dual problems is connected in specific ways. For instance, imagine imagine this primal problem. You have this primal problem, which is of the maximization type. So, you have a primal problem, which is a maximization problem, maximization form. Okay. So imagine you having this. So you have that the primal problem in linear programming typically has the form, the form, we're going to put it in matrix form now. So we have maximize C transpose X, cause some thick C and some thick X, C transpose X subject to AX, cause some thick A and X still, less than or equal to some thick B, then where X itself is greater than or equal to 0. Okay, I mean that's the usual thing we have in matrix form. All right. So here we know that okay, where C is the vector, C is the vector of objective function coefficients, objective function coefficients. So it's the same thing we usually write, just in shorthand form, in matrix form, basically, right? Then that is C, the vector of objective function coefficients. Then we have A. A is the matrix. A is the matrix. I mean, if you remember the Python code, how we write Python codes, this is exactly what we use. So A is the matrix of constant coefficients. The matrix of constant coefficients. Then you have B, which is the right-hand side that you know. B is the vector of constraint limits. Vector of constraint limits. And then you have X itself, which is the vector of decision variables. X is the vector of decision variables. Okay. So that's the primal problem. So again, look at the primal problem right here. So this is the primal problem in short. Now let's look at the corresponding dual problem. So the dual problem now. Now, if since the primal problem is in maximization form, the dual problem will have to be in minimization form, right? So that um we have the dual problem is then derived from from the primal problem, and is typically the dual problem is then derived from the primal problem and is typically formulated. It's typically formulated as a minimization problem, as a minimization problem, which is like this. You have to now minimize B transpose Y. Now, if you pay attention, you see the okay, I mean, it's now B transpose Y. So we have new decision variables Y instead of X like before. But then this B is still the same. Okay, it's a new kind of B actually, you know. But when we do it explicitly, you'll understand what it is. So minimize B transpose Y subject to A transpose Y greater than or equal to C now. Okay. The other time we had AX less than or equal to B. So you see less than or equal to now becomes it's transformed. We have greater than or equal to C, and your decision variables Y will be greater than or equal to 0. Of course, that's the non-negativity constraint. Where now you have Y, you now have Y is the vector, is the vector of dual variables. Vector of dual variables. All right. Often referred. So dual variables are often referred to as shadow prices. They are known as shadow prices or marginal values. Now, I'm going to maybe 2 or 3 videos from now, I'm going to actually solve show how the importance of shadow prices or marginal values as given by in dual problems. Okay, so this is what that is about, right? Well, to actually drive the point home, okay, to drive the point home, I like to do an explicit example, right? So let's imagine we have this explicit example instead of that's the in matrix form now. So let me use the usual form we've always been used to. Imagine this primal problem. Imagine this primal problem, for instance. Okay. And so you have the primal problem, which is usually meant to be maximization, right? So we have maximize z equals 3x1 plus 5x2 subject to then we have the constraint 2x1 plus 4x2 is less than or equal to 8. Then we have 3x1 plus 2x2 is less than or equal to 6. And then we have x1 greater than or equal to 0, x2 greater than or equal to 0. Now, of course, we already know x1 and x2 are decision variables and all of those things. So let's not even stress about that is what that is. So I'm just going to do a very straightforward approach to show you how we transform. I'm still going to do another video after this one to show the importance of how the constraints change, and how the variables actually change to based on the primal problem. Okay, so but here I'm just going to show a very straightforward way of going about it. So these are primal problem, right? Let's get the corresponding dual problem. And this is the way to go. This is the way to go. Now, what you're just going to do is, you see here, the constraints, the right hand side of the constraints are going to become like what is going to form your objective function for the dual problem. What I mean is this. So instead of so you started with x1, x2, right? So now you're going to have y1, y2. Now, the number of constraints you have. So you see, what happens is constraints in primal will result to decision variables in dual. So if you have 2 constraints in primal, you're going to have 2 decision variables in the primal. Then, of course, the number of decision variables you have in the primal is going to correspond with the number of constraints you have in the dual. So it's like constraint for decision variable for constraints, as you're going to see later. And that will be explicitly explained in the next video. So here now, you bring this y here. So you have like 8y1, 8y2. And that is going to become your objective function. So now we have to minimize. So we started with Z, right? So now we have W. So minimize W equals, you see that 8y1 plus 6y2. So that's the objective function now for the dual problem. So the constraint right-hand side multiplied by the new decision variables for the dual, that's what will be your objective function. So now this will be subject to, now carefully, see what's going to happen here. Now you have Y1 and all this now. So like I said, right, decision variables is going to correspond with constraints, right? So we have two decision variables, so it's also going to lead to two constraints. But see what is going to happen. So you're going to have two, so you're going to have um two Y1 plus three Y2. That'll form one of the constraints, and this will now be the right hand side in this case now. But maybe I should do something. I guess I need to use another marker to drive the point home. So now you have 2Y1, plus 3Y2, like correspondingly, and that will be related to this three now. So that means that you're going to have like what you see there, right? That is 2Y1 plus 3Y2. So this two, this three, 2Y1 plus 3Y2. Now the objective function is less than or equal to, right? So now it turns to, or rather, I mean, the constraint. So, I mean, maximization problem are less than or equal to here. The minimization problem becomes greater than or equal to, and that will be greater than or equal to these first three corresponding to x1 now. So to get the other one, right? To get the other one, you're not going to have, I guess I need to change the marker to say something else. Okay. So the other one is going to be 4y1 plus 2y2, and that will be greater than or equal to 5. Okay, so that'll be the next constraint. So 4y1 plus 2y2 is now greater than or equal to 5. Okay, of course, you have your y1 and y2. Y1 is greater than or equal to 0. Y2 is also greater than or equal to 0. In the next video, I'm going to give explicit reasons how, the kind of constraints you have is going to lead to the kind of decision variable you're going to have in the dual. But for now, let's just understand this basic way of of this translation, right? So you have the right hand side 8y1 plus 6y2. W now, you're now minimizing W equals 8y1 plus 6y2, and that will be subject to 2y1 plus 3y2 greater than or equal to 3, and also 4y1 4y1 plus 2y2 less than or equal to 5. And now this is the dual problem. That's just how you formulate the dual problem. So, like I said, next video, I'm going to do something more explicit. But for now, let's move on by talking about the significance of this. So what's the significance of the dual problem? Significance of the dual problem. Okay, so the first significance is that it's very important for resource allocation and cost sensitivity. Resource allocation and cost sensitivity. Okay, so that the variables, dual variables y1 and y2 actually represent the shadow prices, the shadow prices for the resources, and the resources actually represent the constraints, right? Okay, so these values indicate these values indicate the marginal value of the marginal value of increasing the available amount, the available amount of each resource by 1 unit, okay? By 1 unit. I'm going to do a practical example to explain this clearly. But then for now, let's talk about this. Um, okay. For instance, for instance, if y1 is equal to 2, okay? If you know that's y1 belongs to the dual. If you solve the dual and you get y1 equals to, if y1 is equal to 2, this simply means, this is the meaning of marginal value now or shadow price. So if y1 is equal to 2, this means that if we increase, if we increase the resource associated, the resource, if we increase the resource associated with the first constraint, with the first constraint by by 1 unit, the objective value, the objective value of the primal problem, the objective value of the primal problem, which is most likely the profit, right? So the profit will increase by 2 units, will increase by 2 units. That's why it is called marginal value or shadow price. So if you solve the primal, the dual, and you get y1 to be equal to 2. So if you increase the resource associated with the first resource, right? If you increase it by 1 unit, then automatically your profit will increase by 2 units because that's the value of y in this case. So we have that. Then let's go for the second importance, the second use. We have the strong duality theorem. Strong duality theorem. Okay. Now, according to the strong duality theorem, according to the strong duality theorem, if both the primal, if both the primal and dual problems have optimal solutions, if both have optimal solutions, okay, the optimal values, the optimal values of the objective functions, the optimal values of the objective functions of the primal and dual problems will be equal. Okay, the optimal values of the objective functions of the primal and dual problems will be equal. So if both the primal and dual problems have optimal solutions, so like if you solve the primal and you get the value of x1 and x2, which is optimal, and you also solve the dual and you get y1 and y2, which are optimal, the values may not necessarily be the same. I mean, those x1, y1, I mean x1, x2, y1, y2 may not be the same, but the z and w will be equal. That's a strong duality theorem. Okay. So according to the strong duality theorem, if both the primal and dual problems have optimal solutions, the optimal values of the objective functions of the primal and dual problems will be equal. Okay. So what this means is this. This means that solving solving either the primal, solving either the primal or the dual, solving either the primal or the dual problem gives us the same the same optimal objective value. Mind you, just the Z and W, right? Z is equal to W, but X1 and X2 may not be exactly the same thing as Y1 and Y2. That's what the strong duality theorem is about. Okay, so we can then have um, the third significance, and that's related with the weak duality theorem. Weak duality theorem. Okay. So here, the weak duality theorem, the weak duality theorem assures that for any feasible solutions, for any feasible solutions to the primal and dual problems, the objective value of the dual problem, the objective value of the dual problem will always provide a lower bound to the objective value of the objective value of the primal maximization problem. So in the strong law, right, they are equal. But when you look at the weak duality theorem, right, the objective value of the dual, all right, is a lower bound for the objective value of the primal maximization problem. Okay, so in conclusion, right, in linear programming, the duality principle provides a powerful way to understand and solve optimization problems. Okay. Okay, I mean, in this lesson, we demonstrated the relationship between the primal problem and the dual problem using a concrete example. The dual problems gives us valuable insight into resource allocation, pricing, and cost sensitivity. And the strong and weak duality theorems help verify and optimize solutions efficiently. So, I mean, that's how it's been. If you have not subscribed to this channel, be sure to do that right away and hit the notification bell so you can always get alerted each time a new video is released. And don't forget to comment. Let me know if you want me to solve a problem or teach a topic. Then like and share so that more people can have access to this great learning. Till I come your way again, keep optimizing. Bye.